Hi there, in this video we're going to continue our discussion of continuity, and we're going to start with continuity at a point. So what does it mean to be continuous at a point? In the previous video we talked about being continuous on the entire real line or being continuous on the domain of the function. Now what about at a specific point? So we say a function is continuous if the limit as x goes to a and the function value at a are the same. In that case we say the function is continuous at that point. And the continuity checklist that we're going to verify that all these things are happening for a function to be continuous. So in order for a function to be continuous at a particular point, we're going to say at a, f of a has to be defined. So a is in the domain of f. So as in our previous example, right, 3 here for this function, 3 was not in the domain of f, so I can't check continuity there. So I already know it's not in the domain. So that's one of the first things. F of a is defined. So a is in the domain of f. Then the limit exists. So those two things have to happen. And then the third thing is that the limit and the function value have to be the same. So let's look at this example. Determine the points at which the function f has discontinuities. And for each point, state the conditions that are failed. So let's see, where is this discontinuous? So notice that I see right away there's a jump at 2. So I will say this is discontinuous at x equals 2. And why? So which condition does it fail? So let's see. The condition that it fails, let's look at the 3 conditions. The first one is that f of a is defined. So here our a is 2. So is f of 2 defined? What do you think? Yeah, right, there's a solid dot. So we can say yes, f of 2 is equal to 2. So it meets the first condition. So let's go back and look at the conditions again. And you may, if you want to pause the video so you can write this down, that'll be really important in case you don't have the downloaded notes. So f of a is defined, so we check that for 2. The second item on the checklist is that the limit has to exist. So let's take a look. What about the limit as x goes to 2? Does it exist? So let's look at, notice that it doesn't, right? Because the limit as x goes to 2 from the left of the function is 2, same as the function value, but the limit as x goes to 2 from the right of f of x, from the right we are following this side of the function, so the limit is 4. And these are not the same. So we say the limit does not exist. So therefore this function fails the second point on the checklist. So the limit as x goes to 2 of f of x does not exist. Let me move the next example down. Okay, so it's not continuous at 2. It's also not continuous at 3, right? So then we can say f of x is also not continuous. That looks like a W, it's an N. Not continuous at x equals 3. That appears to be a vertical asymptote and there's no dot anywhere. So we can say f of 3 does not exist or is not defined. Right, so this will be it fails condition number 1. F of a has to be defined. So in this case, our a is 3 and f of 3 is not defined. There's no solid dot anywhere. And where else? So 4. At x equals 4, it appears that we're also not continuous. So which condition does it fail? Right, so this one, we can say fails condition 1. At x equals 2 or a equals 2, it fails condition number 2. And what about at x equals 4? So which condition is failed? Notice that f of 4 is defined. F of 4 is equal to 2. So we can also say this continues at x equals 4, which is A. So let's look at what is f of 4. F of 4, let's go back to the function. F of 4 is where the solid dot is. So f of 4 is 2. So that one is okay. Then what about, so that's condition number 1. Condition number 2 is the limit as x goes to 4 of f of x. Does it exist? And we look at the left-sided limit and the right-sided limit. It is going to the same place from the left and the right, so the limit is 4. So that works. So the limit does exist, the limit is 4. But the third condition is that the limit has to be the same as the function value, and in this case they're not. The limit as x goes to 4 of f of x is not the same as f of 4, right? We have that the limit is, this is equal to 4, and the function value is equal to 2. And these are not equal, so it fails 3. Fails condition number 3. So then the function is not continuous at that point. So these are examples of the 3 different types of discontinuities you can have, right? You can have a jump discontinuity. There's a break in the graph like that. You can have a removable discontinuity. So we can redefine this function so that f of 4 fills in that open circle. So we could redefine it. So that's what it means to be removable, that you can redefine the function to fill it in. And then there's the asymptote one. There's a break in the graph because there's an asymptote. And so those create that are 3 main different types of discontinuities. And so these are the different things from the checklist. F of A has to be defined. Likely, if you have a vertical asymptote, it won't be defined at that point. Now, granted, if you have a piecewise function where you then redefine or give that asymptote a point, then you can cross the vertical asymptote, but not usually. You have to make it a piecewise function. The limit as x goes to A has to exist, so that means check the right-sided and left-sided limit. So for this one, I'm gonna write a note here, check 2-sided limits. Well, check 1-sided limits from each side. Check 1-sided limits. Make sure that they're the same. And then the last thing is that the limit so 2 and 3 have to coincide at the same value. So let's try the other example. Scroll down if it lets me. There we go. So determine whether the following functions are continuous at the given A. Justify each answer using the continuity checklist. So I have this 4 examples for you to try. Pause the video, try them on your own, and see what you come up with, and we'll go over them. So it'll be a good idea to write the checklist somewhere that's accessible to you. So if you have a blank piece of paper, write it in there so that you can easily reference that as you're doing discontinuity problems. All right, so for part A, is it continuous at x equals -2? And so let's write what is our checklist? You can either scroll up or look in your notes. And as I said, write it somewhere that is accessible to you. So at x equals A, the first thing is we have to check, does f of A exist? So f of A has to exist. The second thing is that the limit as x goes to A of f of x exists. So what this means, I like to break it down a little further, that the limit as x goes to A from the left is equal to the limit as x goes to A from the right. So that's what it means to check the second one. And then the third condition is that the function value and the limit are the same number. So for part A, we already see that at -2, 1 over -2 plus 2, that's going to be 1 over 0, which is undefined, so negative 2 is not defined. So for f of x equals 1 over x plus 2, right, f of negative 2 is not defined. So it fails condition 1 right away. Therefore, not continuous at x equals 2, negative 2. So I failed the first condition. Let's look at the next one. So b, g of x is this function. Let me copy it and paste it over here. All right, so we're checking at a equals 1. So for a equals 1, we want to check our conditions, right? So does f of 1 exist? So what is f of 1? Let's see, f of 1, where am I allowed to plug it in? So this says when x is not equal to 1, so I don't want to put it in there. It's 0 when x is equal to 1. So f of 1 is 0 based on that part of the function. It tells me specifically when x equals 1, the value is 0. So it does exist, so it passes the first condition. The second condition is that the limit as x goes to 1 has to exist. So let's check it. So how do we check that? We look at the limit as x goes to 1 from the left. Well, in this case, we can just take the limit, because normally if you have a piecewise function, we do that step. But here I can just say the limit as x goes to 1 is going to be of g of x. Sorry, I'm using the wrong variable here. It should be g's. We get so used to working with a particular variable, right? So this is the limit as x goes to 1 of x squared minus 1 over x minus 1. And using our limit laws from before and techniques for finding limits, notice that we can factor this, because if you just plug in 1, you get 0 over 0, which means do some algebra. And now notice that my x minus 1s cancel, which means I have a hole in the graph. And this limit, though, what do we get? Limit as x goes to 1 is just x plus 1. So plug in 1, I get 2. So the limit, does the limit exist? Yes, the limit is 2. So condition 1 is satisfied, condition 2 is satisfied. What about condition 3? Condition 3 says that the limit then as x goes to 1 of f of x, or g of x, has to be the same as the function value. Are they the same? No. Right, the limit, we got it to be 2, but the function value is 0. So then these are not the same. So therefore, the function is not continuous at x equals 1. It fails condition 3. So checking continuity at a point, you really have to check all 3 conditions. But as soon as you failed 1, you can stop, right? Like in this case, in part A, it failed condition 1, so we don't have to check the other ones. As soon as you fail one of the conditions, the function is not continuous. In this part B, the first 2 conditions were met, so we really have to check that third one. Part C, h of x is x sine 1 over x when x is not equal to 0, and 0 if x is equal to 0. So these two are defined very similar. So let me copy it and paste it down here, and let's do the same thing, check the conditions. So now a is 0. So let's check the first condition, right? Does f of 0 exist? Yes. F of 0 is defined to be 0 by the piecewise function. 2, does the limit as x goes to 0 of h of x exist? So I had to change my F's to H's again. So does this limit exist? Let's see. So for this, we have to check the limit as x goes to 0 of x sine 1 over x. We're looking at that since from the left and the right, they're going to be approaching the same thing. So we just look at the two-sided limit. And this is one of those where we have to use the squeeze theorem, because I don't really have a way to solve x sine 1 over x, right? If you plug in 0, you're going to get an undefined here, which is not good. So let's use the squeeze theorem. So then I know sine is between -1 and 1, regardless of the angle. Sine is between -1 and 1, and so I want to build my x sine 1 over x, so multiply everything by x. So times everything by x, so I'm going to have -x less or equal to x sine 1 over x less or equal to x. And now take the limit as x goes to 0. So I'm going to have limit as x goes to 0 of -x is less than or equal to the limit as x goes to 0 of x sine 1 over x less or equal to the limit as x goes to 0 of just x. And now I can plug in, right? As x goes to 0, this side will go to 0, and this side will also go to 0. And so I end up with 0 is less than or equal to limit as x goes to 0, x sine 1 over x less than 0. So then what can you say? By the squeeze theorem, this limit must also be 0 by the squeeze theorem. And so now I have, does the limit exist? Yes, it is 0. And the third one is, are they the same? Are the limit and the function value the same? And yes, they are. So I can say condition 3, the limit as x goes to 0 of h of x was 0, which is also the function value. So what can I say? Therefore, h of x is continuous at x equals 0. Pretty cool, right? So this one met all the 3 conditions. So now let's look at D. So that one, is it continuous or not continuous at pi? So let me copy and paste it. If I went too fast on that one, that's the beauty of videos. You can pause and rewind and go back to look at what we did here. So the squeeze theorem is from the previous section, so hopefully you have had time to get familiar with it. And now here is just an example in practice. Practical example is what I meant to say. Okay, so what about this one? Is it continuous at pi? So A is pi, so we're going to check the conditions again. So 1, does f of pi exist? And so how do I find it? F of pi is equal to, which function are you allowed to plug pi in? I'm not going to plug it into both, right? Because then I wouldn't, if I'm allowed to plug it into both, I don't have a function. Remember, functions have to pass the vertical line test, meaning every input gives you one output. So I should only be able to plug in pi in one of these. And I go to the one that has the equals. So greater than or equal to, right? That includes pi. So it's the bottom function. So f of pi is 75 to the pi minus pi, which is 75 to the 0 power, which is 1. So does it exist? Yes. So pi is in the domain. The second one, second condition, does the limit exist? Does the limit as x goes to pi of k of x exist? I did it again. I put f's there instead of k's. So this one is defined differently than the other two. Right here, it was just when x not equal to 0, so the two-sided limit. So from the left and the right, they're approaching the same thing, and same for the other one. That was defined that way, not equal to 1, right? That means that from the left and the right, they're approaching the same thing. But for this one, from the left, we're following one function, and from the right, we're following a different function. So I do have to split them up into their one-sided limits. So I'm going to look at the limit as x goes to pi from the left of k of x, and the limit as x goes to pi from the right. And so from the left, which function are we following? If you're to the left of pi, you're smaller than pi, so less than. So I'm following cosine x plus 2. So this will be the same thing as finding the limit as x goes to pi of cosine x plus 2. So plug in pi. I'm going to get cosine of pi plus 2, which is 1. Right? So the limit exists. What about as x goes to pi from the right? So from the right, we are following the other function, 75 to the x minus pi. Right? If you're to the right of pi, you're bigger than pi, so more than. So x is greater than or equal to pi. So 75 to the x minus pi. And so this gives us, plug in pi, you get 75 to the 0, which is 1. Are they the same? Yes. So that means that the limit exists. So does the limit exist? Yes. And now the third condition, are they the same? Are limit as x goes to pi of k of x and f of pi the same? So that's the third condition. And yes, they are, right? The k of pi was 1 and the limit is 1. So therefore, they are the same. So yes. And so we can say k of x is continuous at x equals pi. And in fact, in this case, well, it is continuous, but we can see that it is right continuous. So a function is called right continuous if the limit as x goes to pi from the right is equal to the function value. And it is left continuous if the limit from the left equals the function value. So I'll talk about in my next video, the left continuous and right continuous.